In our sixth problem, we are given with a series, or rather the sum of a series 1 upon under root n square plus 1 plus 1 upon under root n square plus 2 plus 1 upon under root n square plus 3 up to 1 upon under root n square plus n. And we want to find the limit of this series or the limit of sum of this series as n tends to infinity. Now this is a very special type of problem and a very important problem because it involves the concept of sandwich theorem. Now these type of questions cannot be solved by the normal regular methods. Instead they require a special approach. Now what we do is, we call this as f of n, which is equal to 1 upon under root n square plus 1 plus 1 upon under root n square plus 2 plus 1 upon under root n square plus 3 up to 1 upon under root n square plus n. Now n square plus n is greater than n square plus n minus 1, which would be the denominator of the previous term, and it would be all greater than n square plus 3, would be greater than n square plus 2, would be greater than n square plus 1. That is, n square plus n is greater than n square plus n minus 1, would be greater than n square plus 3, would be greater than n square plus 2, would be greater than n square plus 1. Hence 1 upon n square plus n would be less than 1 upon n square plus n minus 1, would be less than 1 upon n square plus 3, would be less than 1 upon n square plus 2, would be less than 1 upon n square plus 1. Now what we see is, if we put under roots in all the denominators, we see that the series, we'll get the terms of this series. Since this is the greatest term and this is the least term, we see that the terms are getting decreased. There are n terms of this series. So let us consider another function g of n, which is equal to 1 upon under root n square plus 1 plus 1 upon under root n square plus 1 again plus 1 upon under root n square plus 1 again n times. What we have done is, we have replaced all these terms apart from this first term by the first term. That is, we have taken n times the first term. So we get g of n is equal to n upon under root n square plus 1. Now what we do is, we again consider h of n, another function, and take it as 1 upon under root n square plus n, which is the last term, plus 1 upon under root n square plus n times. In the similar way, as we took 1 upon under root n square plus 1 n times in g of n. Now this becomes n upon under root n square plus n. Now what we see is, 1 upon under root n square plus 1 was the largest term of this series, and we have taken this largest term n times. So this is greater than this is greater than this, and obviously the last term would be greater than this term. So the sum of this series g of n would be definitely greater than f of n, because the largest terms have been added n times in g of n. In the similar way, we have taken the smallest term n times in the function h of n, and the smallest term has been added n times. So this is less than this is less than this, the third term will be less than the third term of this series, and similarly the nth term of this series will be less than the nth term of this series, or rather they will be equal to nth term of this series. So the sum of these n terms will be definitely less than the sum of these n terms, because smaller terms are being added to get h of n. So h of n will be less than equal to, or rather less than f of n. So what we see is, we get f of n is lying between g of n and h of n. This gives us a hint of sandwich theorem. In sandwich theorem, if we want to find the limit of a function f, we try to find out two other functions in between which the function f of x has been sandwiched. We try to find out a function g of x greater than f of x and a function h of x smaller than f of x in such a way that the limit of the function at the given point gx is equal to the limit of hx at the given point. If the two limits are equal, then the function fx, which is sandwiched between the two functions g of x and h of x, the limit of this fx at the given point will also be equal to that the limit which g of x and h of x are attaining. Now we try to check whether this h of n and g of n are having the same limit or not at n tending to infinity, because we want to find the limit of f of n at n tending to infinity. We have found two functions between which f is sandwiched, but we can find many functions between which f of n can be sandwiched, but we need to find those two specific functions whose limits at the desired point is equal. Now n tending to infinity, we'll rub all this. We just want the final value of h of n and g of n. We'll write this again. G of n is equal to n upon under root n square plus 1. So we try to find out the limit n tending to infinity g of n, which is equal to n upon under root n square plus 1. For this we do n equals 1 upon t. Now n tending to infinity means t is tending to 0. So this becomes limit t tending to 0, 1 upon t square plus 1. So this becomes limit t tending to 0, 1 upon under root t square plus 1, which becomes equal to 1. Now we try to find out the limit of h of n as n tends to infinity. It will be equal to limit n tends to infinity n upon under root n square plus n. We try to find out this limit in a different way so as to get both the approaches to find the limit of any function as n tends to infinity. We can also use this approach n equals 1 upon t, but we will see a different approach. What we do is, again as I said earlier, if we have any square roots or cube roots or fourth power etc. in the numerator or denominator, then what we do is we first check the highest power or the highest term of n inside the square root of the cube root, which is n square in this case. So we take this n square outside. This n square will come out as n. So this becomes 1 plus 1 upon n. This n and n gets cancelled out. As n tends to infinity, 1 upon n gets 0. So this again becomes 1. So we have found out two functions g of n and h of n between which our function f of n has been sandwiched, and the limit of gn at n tending to infinity is equal to the limit of hn at n tending to infinity. So by sandwich theorem we can say limit n tending to infinity f of n is also equal to 1, which is our final answer.